Okay, it's 4:03. How about we get started? And do you want to start the recording, Ella?
It actually is. I'm
Or it's
just going
finished?
to
Okay,
chop
great.
it starting now
Okay,
when I
cool.
send it out. Yeah.
Great. Well, welcome everybody. I'm going to go ahead and start sharing. My name is Rich Stromberg. I am the current chair of the PV Technical Division at American Solar Energy Society. And today I'm going to cover a lot of cool stuff about infrared thermography. And I've tried to structure this both for whether you have a small single family home array or commercial or even a larger scale system. What I'm sharing is going to be applicable to everyone of all these different array sizes. So there's different budgets you can do these things, and I just want you to understand how it works and what your options might be if you think you might want to inspect your array or arrays with infrared cameras of various sorts. So here's my contact information. You can reach me at restromberg@alaska.edu. I am physically based in Colorado, but I'm doing my PhD through University of Alaska Fairbanks, sponsored by the great people of Alaska Center for Energy and Power. Our agenda for today is I'll show you how to join if you haven't already joined ASES, and then we'll get into the basics of infrared light, and then PV modules and infrared light, and uh, how it will emit different types of heat under different conditions. We'll show you some typical defects you would expect to see and issues with infrared wavelengths. And we'll get into some of the equipment that's available and what its sensitivities are a little bit, several slides on aerial thermography, so drone based. And then if anyone at the end has any perplexing or interesting issues they've seen in the last quarter, there's time to share with that on your observations or head scratching issues. And let's have the collective give you feedback and see if we can't figure out what's going on, what you're looking at. So you've got me right here. Okay, so to join ASES, real easy. You can go to the main page and there's a join link. Here's the direct link right here, and it's a screaming deal. Regardless of your budget, even if you're a student, and Madeline, you are at Western. Western is an ASES college chapter, and they have funds through the club council to pay for your membership as well. So hit them up if you want to join. And everyone else, you can go online only and save some paper. That's what I prefer to do. Auto renewal as well. It's just so easy. And some of these are down in the $25 range for the kind of lowest level. And of course, if you want to sponsor us to higher levels, we have great opportunities and great appreciation for folks who can do that too. So that's it on joining ASES. Now I wanted to talk about, in fact, here I'm going to switch over to a little bit larger screen here. So I think some of you might have heard of William Herschel. He was a scientist in the late 1700s, early 1800s, actually studied quite a few things. He worked a lot with optics. He built telescopes, and he was actually uh, uh, he's probably best known for discovering a planet that he called Georgium Sidus after King George III. That didn't last, so you know the planet as Uranus. But so he discovered that from doing nighttime surveys, and his work with optics really helped him to kind of understand um, prism effects, just different shaped lenses, what it does for you. And he actually used these different optics to look at stars and understand what different wavelengths am I getting off the stars? And what does that tell me about maybe their makeup? And are they all the same or no? They're actually different kind of categories. So he's had that optical background. And here you can see he's actually shining inside. He had a portal to send light from the outside, and he'd experiment around with the different wavelengths of light. And he had this hypothesis, he said, or at least a question of, hey, I wonder if different colors of light as the prism breaks them up are the different temperatures. So by doing that, he set up multiple thermometers to catch and aim the light so that each thermometer would measure the temperature of that wavelength of light. And like a good scientist, he had a control that he placed to the side outside of the rays of light that were split out from the prism. And what did he find out? This is why you design your experiments with controls and stuff. This that was way out here, where as far as he could tell, no light was shining, that was the hottest temperature of all. So he deduced from there of, oh, there's still something there that's coming through the prism. I just can't see it. And so from that, he eventually deduced that, oh, there's this other band of light that is in a color range I just can't see. And so that was the beginning of infrared. Just for your information, your typical visible wavelength of your eyeballs is between 400 and 700 nanometers. They actually slip a little bit down below here. This is technically into the near ultraviolet, and this is getting up close into the near infrared. But 400 to 700 is visible by all people's eyes. And then you can see UV is shorter wavelength. So the wavelength is like the space between the peaks and the width there. So the higher energy has shorter wavelengths. Longer wavelength is get really long, like radio waves. Here's AM radio is 100 meters long from peak to valley back to peak. That's 100 meters. So really long wavelengths there. But some of the radio waves in the FM is down at 2 to 5 meters. TV is a little bit less than 1 meter. Radar starts getting lower down into the centimeter range. And then we have infrared that begins here at about 850 or so. 800, 850 is near infrared. And then on up to about half a centimeter. And then X-rays are down here and gamma rays. These have the highest energy. So he discovered infrared light. And it's the infrared light, since he was picking up the greatest amount of heat, that is really ends up being a great wavelength to detect and actually quantify and measure heat if you have the right kind of sensor on your camera and it's calibrated. Okay. So typically we have, here's the sun. We should all recognize that, unless you live in the Pacific Northwest this time of year. You might not have seen it for a while. But so let's just imagine it's a sunny day and you have the full amount of sun shining down onto your field where you've got your solar array. So here, the ground will reflect this. This is like tundra grasses. This is got people looking to come in. About 15% of the light that hits kind of a grassy, this is a tundra up around Kotzebue, Alaska, it will reflect about 15% of that light, and then the rest is just absorbed by the ground as heat. Solar panels, the newer ones, since about 2005, they only reflect off the surface. Even though it's glass, they only reflect about 5%. And that's because manufacturers started putting an arc or an anti-reflective coating layer on top of the glass. I think a lot of cells, the silicon cell itself also has an anti-reflective coating as well. But the module can let 95% of the energy come in, only 5% gets reflected off the front surface. Here's typical module. This is not the newer bifacial that has glass on the back sheet, but you start with aluminum frame in the front, tempered glass that you can touch when you walk up to it. There's a very thin, transparent encapsulant. This encapsulant happens to be made of ethyl vinyl acetate, which for short they call it EVA, but there's other kinds. There's a polyolefin and a few other materials. The solar cells where all the magic happens, that's right here. And then on the back side, there's another encapsulant layer then your opaque back sheet, which a lot of times is white, but some module manufacturers put a black solid back sheet. And then you got your junction box and your cables. So that's your typical module, what it looks like. And then the cells all run in series. If you just had like batteries and say these are D-cell batteries and a flashlight, each one's 1.5 volts. But if you stack them together in series, that adds up the voltage. So this would be like these three would be 4.5 volts of power. Same thing goes with a solar cell. Each solar cell generates about 0.5 voltage of potential. And so if you start running them in series back and forth, however many cells times 0.5 volt, that's about what you would expect to get out of that module. But we can't stack them on top of each other because this top cell would block all the sun from hitting the cells below it. So we have to spread them out on the module so all of them can get the sun. And then actually how they're connected together is there is the front bus bars. The smaller lines are grid lines, and then the thicker lines are bus bars. And we'll have a strip of silver tabbing material that will lay on top and get soldered onto this front bus bar, and then it will extend underneath the cell next to it, and that gets soldered in place as well. So that's how you make the connection of one cell to another, kind of a daisy chain. And then here's what it looks like. Here I can actually see this top. I can see there's kind of a break. And so here's the silver tabbing that starts here on top of the bus bar, same width, and then drops beneath the cell next to it. And then here's the next cell that has the tabbing on top, but then it connects to the backside. So that's kind of how that works. And then what we get is your final module. This is a pretty typical 72 cell module, and they'll have these what they call substrings. So here's 12 cells down, 12 back up. So that's 24 cells in series here, another 24 in series here, down and up, and then a third down and up. And then they meet in the junction box. And in the junction box, there's actually a diode that, let's say this part of the module was shaded, that diode would keep power from these other substrings back feeding into the shaded cells, which if you shade a cell, it'll have essentially 0 volts, and voltage likes to go from higher to lower. So it would suck the power from the whole module if they didn't have these bypass diodes to kind of separate out different parts of the module. Or if there was some other defect that damaged the cell here, it would still allow the other two substrings to work. So that's how most modules are made these days. Now, here's the typical layout path, and this particular module, there's an example. It was one I was looking at a couple of weeks ago, and its normal open circuit voltage before you actually connect it to feed a load is about 46.7 volts on the data sheet at nominal temperature, being 25 degrees Celsius, which is 77 degrees Fahrenheit. So normally all these cells would be producing a certain amount of power, but here's one with a failed diode. One of the 3 bypass diodes is bad, and so this will actually see a few degrees warmer. It'll be about 4 or 5 degrees Celsius warmer than the other substrings. And when we use a thermal camera, we'll be able to pick that up. So here's how a typical well-functioning module would perform thermally and electrically. And let's say this is a relatively current module. To make the math easy, I just picked 20% efficient. And what that means is if you have full sun, which is classified as 1,000 watts per square meter, and let's say so that's the amount of energy. And let's say this is like you've got 2 square meters. So you've actually total got about 2,000 watts total hitting this instantly, but per square meter, it's 1,000. 5%, remember, is going to reflect off the front because there is that glass, but there's the anti-reflective coating. The remainder, we've got 95%. Well, 20% of that total amount of that's hitting the sun, coming down from the sun, 20% of that is actually getting converted into electricity that feeds either your house load or gets sent out to the grid. And then the remaining 75% causes the module to heat up. more than if it was not in the sun. So the module temperature will raise about 20 to 25 degrees Celsius higher than the ambient temperature when it's getting full sun. So this is a fully functioning module. Everything's great. We would expect to see this out in the field on your arrays. Now, let's say the module it's completely broken, or maybe somebody cut the cable or disconnected the cable so it can't send its power out. Well, now none of that 20% of the power that we had here can go to the grid. And so the module actually heats up more. All that 95% of the energy stays in the module, and it has to radiate that heat out to dissipate it. So the module will actually, the entire module will be about 4 or 5 degrees Celsius warmer than the adjacent one if you were to look through a thermal camera on multiple modules on your rooftop or on a ground mount array. And then this would be if there was one of the substrings that wasn't producing, most likely due to a failed bypass diode. You would see that instead of 20%, you'd get 2/3 of that total power going out to the grid. And then this part of the module would heat up more. This wouldn't. So you would actually be able to see a temperature difference across the module on this substring versus others. And then also another common issue that we might see is one cell that's just bad and it's hot, it can actually pull power from the rest of the module. And in this case, it might not produce any power out to the grid, and it also dissipates heat, but you'll see this cell being quite a bit hotter. It'll be more than 5 degrees warmer than the adjacent cells. I've seen it be 50 and even 60 degrees Celsius for really bad hot cells. I'll show you a photo of one here later. But so that's another signature that you would see, just one single cell or two cells that are hot. So, one thing I wanted to mention too is the front is glass, and technically glass does not allow infrared light to transmit through it. But what that means is, let's say you're outside of my house and you're pointing a thermal camera at me. If I'm standing behind the window, you can't see me because my heat doesn't transfer through to through that glass to the person holding the camera on the outside. But what happens is, since all these layers are stuck together, instead of having a radiant heat from my body trying to go through the window glass and it's blocked, here there is a direct physical connection, and so you get conductive heat transfer from this hot cell into the glass. Now the module should be running for 15 or 20 minutes like that before it's had enough time for that heat that hot cell to heat up the glass right around there, or conversely warm up by another 4 to 5 degrees the substring. But that's how you're able to see it. Now, if you walk around to the back side and look, aim it at the back sheet, you would see these a little bit clearer. You get a higher temperature reading, and you'd be able to see it sooner. But just know that yes, glass does block infrared light, but when you have that direct conductive transfer of heat from the cell to the glass, that's how we're able to actually inspect the PV modules. So yeah, we define a hot cell as any cell that's more than 5 degrees hotter than adjacent cells. And then, so this is a hot cell. You can see the rest of the module is averaging 19.3 degrees Celsius in this range, but this cell here is 52.6. So you've got 32 or 33 degrees hotter on that cell. That's something that we would consider that a safety issue, and you really need to take that out of service. If your module's still under warranty, ask for a warranty replacement through your installer. But hot cells over time could continue to get worse. And so if they could get worse, we'd rather take those out of service. It's certainly not going to produce as much power, and we just don't want safety issues on solar arrays. Now, the one next to it is a very clear signal here. And here's the thing about your infrared camera is it will kind of auto scale. So you can kind of see some really blue sections, and that might be the ground or something other than the module. But just because you see red of itself is not a problem. It's what's the other temperatures that you're seeing and what's the scale across that. Because it'll just go min to max, but if the module is very uniform and only about 3 degrees Celsius temperature difference, you'll still get a pattern. So you got to look at what do the actual numbers tell you. So this one, though, it shows us this part of the module is 17.7 degrees Celsius. And then here, look at this, is 1/3 of the module is 22.3. So that's, we've got about 4.5 degrees Celsius warmer. And this tells us that, hey, we know we have a bad bypass diode that's isolating this 1/3 of your module output. Again, something like this would be worthy of filing for a warranty claim with the module manufacturer. Another thing I'll point out is a defect like this, the bypass diode failure. You probably would never see that on original commissioning when the installer first built your array, whether it's a small array or a large one, and then you go through the commissioning process. It's doubtful that you would ever see this happen. It's more like 6 months or so down the road is when you might see that bypass diode start to fail, and then you'll see something like this. So I actually like to inspect solar arrays, wait about 6 months after they're installed, and just check them and make sure everything's running right, and there was no early burn-in failures of any of the products in the system. So here's something else that you'll see. This is actually on this, you can either see dirt debris. I happen to remember
Hello.
this. Yep. This particular site has its pollen that's collected on the downhill side of the
You wanna
module.
take a shower?
And so it's actually blocking some of the sun from hitting these cells, and they're getting hotter because it's shading them, and it's what we call a reverse bias of that cell. So it's getting extra power from the adjacent cells feeding in, and it's getting quite warm along this section. So you'd think, hey, the sunlight should be able to go through there. Well, once that pollen or dirt gets thick enough, you'll actually see this with your infrared camera. So if it's bad enough to start picking up a signal that's pretty noticeable, then you should, in fact, here, this is 7.1 degrees Celsius here, 15 degrees here. You should definitely try to clean these modules off and see if that goes away. This here is a leaf that's landed on this module as well, but you can see bird droppings will also cause shading on individual cells. And if you're getting a heat signature, it's worth your while to clean off that cell. You don't need to do all the modules, but this one will be fine. And then this as well. So back to the bypass diode failures. On this module, you can see the left side here is a bit warmer. If we walk around to the back side of this module and look on the junction box, here there's like a left, middle, and right. And so the right bypass diode is showing up hot in the junction box, corresponding with this same substring that you can see that's warmer as well. So that's another way to use thermal energy or thermal imaging to detect an issue with your module is on the backside. And then this is another one that the entire junction box, all three of the diodes in this different style of junction box are showing a heat signature. And yeah, that module's not producing. We would want to take it out of service. Again, if it's still within the product warranty, which is product warranty is typically 5 or 10 years. It's different from your power warranty, which is a 25, 30-year warranty on your modules. But take that out of service as well. If it's still under warranty, try to get it replaced. This is this is a system I looked at in Denver. It's rooftop commercial, and it's kind of low angle, 10-degree tilt ballast mounts on all these modules. And there were two pairs that you kind of see this mixed pattern of hot and cooler cells. So something that's happened is either you have one or both of the modules are short circuited, or there's a short circuit in this case, it was two modules connected to a single DC optimizer on a solar edge system. So I'd say most likely, my first guess would be test it with a different DC optimizer and see if the problem goes away. It could still be the modules, but it also could be the DC optimizer. But you can see there were two out in this field. The rest are all looking fine. The fact that this is red and these are like yellow and green, that's not a huge issue because it's part of that auto scaling. And this is so much farther away than here. There's no problem with this module, but this pattern says, oh yeah, you definitely have an issue with these two module pairs. Something that's common to see, and you shouldn't be concerned about it. And again, this is some auto scaling. So the module itself, 19 degrees Celsius. Right here at this point, it says 22.8. So it's less than 5 degrees. It's fairly common to see wherever the junction box is on the back side of the module, that will dissipate heat slower than the rest of the module that doesn't have that junction box and greater thermal mass. So you'll see it typically be warmer at that point. And if it's less than 5 degrees, nothing to worry about. But just know that, yeah, you'll probably see that on some modules. If you want to look for more information on some of these defect types, the International Energy Agency, PVPS, which stands for Photovoltaic Power Systems Group, Task 13, of which I am now a member, they wrote this report back in 2014, updated in 2016. I think there will be a newer one coming out, but they do have section 5.3 on thermography itself. One thing that's important to know when you're doing these inspections is the modules have to be connected into a system and producing power to be able to see something. If you just have a module that's not connected to anything, there's no current flowing through it, you're never going to see a signal. It will just stabilize out to whatever the ambient temperature is, plus about 20, 25 degrees Celsius, because it's whatever sun is hitting it to increase the thermal mass of the whole module. So, and then short circuit mode is an option. Let's say you just have a module you pulled off a pallet. You can try point it towards the sun and plugging in the positive and negative of that single module together. It's safe to do that on a single module. Don't ever do that on more than one module because that is just so much more power going through. But you can sometimes find defects by putting them in short circuit mode and leaving it there for 10, 15 minutes. But sometimes you get kind of that mottled pattern of that looks like this, depending on the module type. And it's very nuanced of trying to detect, hey, what's really going on here. The best is you already have a system that's in place and you go up with your camera and you start looking at it. That's the easiest way to detect stuff. In this document, again, there's a link to it here. It's great. They have non-infrared detected images as well in this guide. So I think it's a great document. Go ahead and download it. It makes for great reading if you're a nerd like me. But they have a section in here where they show, like, this is a great example of one module is warmer than the others. And so this whole module is not sending its power out to the rest of the system. It's not sending it to the inverter. So there's probably either a failure in the junction box or there's a broken cable kind of thing. But that's the whole module is, again, about 4 or 5 degrees warmer than the adjacent ones. Here you can see, again, here's one of the substrings. That's also a 4 to 5 degree Celsius temperature difference. This random pattern is, this is kind of the pattern you would see when they're in short circuit mode on some modules. So it would look like that. If you have more of an edge effect, that's a thing called PID, or potential induced degradation, in which case kind of charge can build up around the edge. There's two kinds. One is static charge, and you might see this on a long string of modules that's at least 1,000 volts on the string. You'll see it even more commonly on 1,500 volt strings. And at either end of the string, either the very positive, very negative end, the potential between the ground can get great, and you get static charge buildup, and you'll see this pattern. You can also get it, and I say negative because some strings are actually wired to negative voltage on some inverters. Others, it's just all 0 to positive 1,500, but there's some that you'll see half are 0 to positive 1,500, half are 0 to negative 1,500, how they wire them up. This just ends up being what the inverter designers selected to do. There's another kind of PID where if you have sodium contamination in the edge seal that goes around the glass in the frame, that can also cause a potential difference. But sodium travels through silicon very easily. It's a contaminant. It adds extra charge, and you'd also see something like this. And then I mentioned like one hot cell would look like this. Let's see. Okay, connectors. You can also use your camera to inspect connectors. And here's kind of typical, all the different pieces of the cross sections. We really don't want to ever mismatch, even though physically you can plug in a bunch of different connector types. If they're not the exact same label from the same manufacturer, you risk getting poor connection here. The plastic will seat up, but the actual internal plug-in socket may not make good connection, and over time get higher resistance and arcing. And that's actually the number one cause of fires on solar arrays is poor, either you didn't plug in the connector all the way or you mismatched them, that over time it can cause arcing. And here's some thermal imaging where you can see this is an MC4 connector plugged into an MC4. That's great. These are all the MC4 on this side, but they plugged in a couple of different manufacturer type of connectors that the plastic fits, but they don't have good contact. And you can see how much hotter, this is 330% higher temperature on this connector than what you would expect and desire. And it can get bad enough to start melting them. Once it melts, then you can just have open connectors, and that's when you get fires. Okay, so what kind of cameras could you get? FLIR is a great manufacturer. I don't have a lot of money as a PhD student. I cannot afford FLIR unless I have grant funding. If you get grant funding, great, go for the top of the line. It has the best calibration, the longest reliability of a camera. Great, go for a FLIR, or if you have the cash, go for that. But you know, you can see here's a 240 by 180 pixel infrared camera for $2,400. Now, if you're a PhD student like me, you can go with, this is a, the infrared on this is actually, that's the display, but I think the imager is, oh, this is like 160, yeah, this is like a 160 by 180 or 190. This here is 192 by 256. So exactly comparable with the FLIR, and it's $240. It's a HT 18 plus. It's made in China. I've ordered them from AliExpress. They come in just fine. A really nice thing about these, the image is good. It has both a visible and a thermal camera in it. You can store pictures, transfer to your laptop through a USB cord. The really nice thing is when you leave one out in the field and it rains 2.5 inches, and you don't realize till you're 4 hours away and you get home, it's like, where's my camera? And it's rained on it and damaged it. I only lost a $250 camera than a $2,500 camera. So it's if you're like me and a little bit absent-minded sometimes, this certainly much more affordable. But you can see there's a price range, and maybe if you just have a home system, you don't want to do this, but maybe you and your neighbors, if you're curious, might want to share one and use that between you. And then there's drone based. So this is a drone I have. This particular camera, it's several years old on this drone. It's only 160 by 120 pixels. So not even as good as this, and not quite as good as this camera here. There are newer ones that are 640 by 480 pixels. And so the higher you are above an array, typically the distance from the light source, and that includes infrared light source, it's harder to detect. But with the 640 by 480 sensor on the $6,000, $7,000 drones, you can detect these issues from farther away. My drone, I can detect a lot of stuff at 60 meters height above the array and everything at 17 meters above the array. So I've learned to just kind of fly along and scan over, and I can quickly see if there's anything different. I need to slow down, back up, maybe even get closer to take a photo. But so there are drone systems. Mine was about a $2,500 instead of a $7,500 drone that I got off eBay. So IR cameras themselves, remember there was the visible light, and then Herschel, William Herschel was just looking at this near infrared, which is kind of in this range. It says near infrared, shortwave infrared, medium. Most of your cameras, like the handheld ones I showed you and the drone based, will be in this long wave infrared from 8 to 15 microns. So microns a lot here. This is in nanometers to 700 nanometers. 1,000 nanometers would be your 1 micron. And so it's in this wavelength that they're able to get a good reading and have it calibrated and know that, okay, if it's this wavelength, it's this temperature kind of a algorithm that they use. So it's important. It's best to use it on a sunny day, although in some locations, I've been up in Alaska for weeks when we didn't have enough good sun, and I've had to do thermal imaging as low as 40 watts per square meter. That's only 4% of full sun. It's not ideal. Really, you would like at least 600 watts. There's actually technical guidelines and specs that have been adopted, and if you're doing calibrated measurements, it needs to be greater than 600. But and if you've got full sun, you're going to get that, great. But just be mindful of, if it's a cloudy day, you may not pick up subtle differences and might want to come back and look again on a sunny day when you have the opportunity. And then the instructions are really real simple. They'll tell you how to take a photo, how to save the photo, how to export it. They're very simple to use, but these are some examples there. And then, yeah, I'd mentioned there's an auto scale function on all of these cameras. So you can't just look at the color and say, oh, red, there's a problem. No, it's like, what's the minimum and maximum across your viewing area or across the module? And let that temper your interpretation of the image. And then also you need to be conscious of, where's the sun shining? This is here, it's like, oh gosh, we have the module is 42 Celsius, but we're 60 degrees Celsius warmer. Well, this is actually, if you look in the visible wavelength, we just have the sun that's reflecting off of that module. So I need to just change my angle of where I'm at relative to the module I'm trying to image. And here's the same module, and I just kind of moved over an angle where the sun wasn't reflecting into my coming in off the module straight into my camera, and you can see everything looks fine. So just be mindful of where's the sun when you're doing your imaging. And then here again, as I say here, you want image modules while the array is producing power. You can photograph anomalies on the front or the back of the array or of the modules. And in fact, I think these are all front side on these images, but actually, I think this is a backside image here as well. This is a short circuit pattern, again, open or a bad diode, and then you've got either soil collecting along that there's like a lip on the metal frame that sometimes water will pool there and it won't shed off, and it's common to see dirt, dust, and sometimes pollen gathering there. Now here's some aerial images taken with my drone, and a couple things to notice. One is that the temperature doesn't line up. This is 60 meters elevation above the array. So this is actually should be right over these modules, but there's a parallax a difference of exactly where the thermal camera is pointed and the visible camera is pointed. And this is off at this elevation by about 2 meters, because these modules are 2 meters high. So you should just be mindful of that, that when you're farther away, you can get that effect that the parallax is going to be more noticeable. But we can see, hey, it's much brighter here in this yellow and much brighter here. The blue actually is the shaded space in between the rows. But this tells us, hey, we've got an inverter, because there's a whole bunch of these strings. When I look down the line, there's a total of 8, 4 on each row, and they were all brighter. So we need to go check the inverter. The inverter was in a fault state. So none of these modules were able to send out their power. Here's an example. Again, this is the other end of those 2 strings I showed you before. Here's another, just a single string of like 17 modules or so that are warmer. So we went back to this separate inverter and we checked all the fuses going in. In fact, we were able to tell, we had a layout map. We knew this was like string 7 and this is string 8. So we checked the fuse on string 7 and it was a bad fuse. So we replaced the fuse, and then this substring or this string of modules started producing power. So we were able to catch that real quickly. And then notice that this is the same string, but as I went down to 30 meters, the parallax now is only about 1 meter off, because about half a module length. And so that's what's going on there. This is down at 11 meters above, and we have a hot cell. And so there's almost no parallax here. And so I went up and inspected. That's one hot cell, and we removed that module out of service. And then this was 3 separate modules adjacent. When we went in and looked at them, it's actually just one module that had a bulged melted junction box, but it failed in such a way that it was actually sucking power from modules to either side. And so that's why they all were showing kind of this pattern. And when we took that out of service, everything was fine. Here's with my drone, you can see we've got, this looks like 2 substrings that are failed. So we want to replace that. And so that's all the images. To sum things up, what you can and cannot detect with infrared thermography is you can certainly see when you have inverters or DC combiners of many strings coming into a certain box. You can tell when those are offline. You can tell when there's an open string, a isolated or open circuit within a module, failed bypass diodes, hot cells, high resistance connectors from looking using your infrared camera on the backside, PID kind of related losses because they show that pattern, or excessive soiling and shading. What you won't see, so just because you don't have a thermal signal doesn't mean that everything is perfect on your array. You still need visual and other methods to check, mostly visual, but electrical measurements as well, to detect silicon microcracks, delamination, any power degradation not related to PID, discoloration of the encapsulant layer, or backsheet damage. So we can see it tell you a lot, and I like it as a good first pass. And then you kind of know, I like to map things out and know, okay, we have problems here. Let's walk over there after we finish scanning around. So that's what I typically do. So we'll open for Q&A on infrared, and then also if people have observations, issues with systems they've encountered, bring them up. Let's talk about that and see if we can figure it out.
Thank you so much, Rich. That was great.
Remy says, oh, let me just open up the chat here. Oh, in fact, we had a few other things in the chat. What is the state of the art of capturing the otherwise lost thermal energy in solar panels? There's I think theoretical you can start stacking cells and stuff on top of each other, multi-junction cells. There's some other, in fact, you're starting to see more common, a combination of silicon and people trying out perovskite layers and stuff, but you'll hear of heterojunction technology and just multi-junction cells, and you can get up to about 38, even 40% on those. That's kind of the upper limit. But yeah, you're catching more energy that, in fact, the higher energy photons, let's say it's a 400 nanometer, so that's higher energy, it can go all the way through that silicon cell. So if you have another cell underneath it to give a second chance for that same photon to create some energy, that's why you see stacked cells sometimes. But yeah, there's just always that lost thermal energy. I think some of the aqua voltaics of like photovoltaics, they call it, of the floating arrays, being on top of water, they'll operate cooler and you get more power. But there's still, I think, some of the same limitations. It's just harder to warm them up. Warmer modules produce less power, cooler more. So you have that benefit. But I'd say with these multi-junction cells, about 40% or so is the maximum. And you're always just going to have some heating. A typical coal plant, if you're burning coal, is only going to take about 35% of the heat that's generated from burning that coal to create electricity. The remainder goes up the stack in the form of heat and radiates out from the combustion chamber and doesn't produce any electricity. So just for comparison, your automobile engine, especially for automobiles, about 20% efficient of the energy in the fuel when you burn that. Only 20% of that energy goes towards moving the vehicle and its contents. And then the rest goes out the exhaust pipe or radiates out from the engine block too.
Hey, Rich, this is Carly. I have a question. With that in mind, is there a concern for large solar arrays contributing to the urban heat island effect?
So there's a fella that uh, I try not to engage in too much on LinkedIn, and I won't share his name, but so there is an issue there. And basically, when you consider what you have to calculate, what is the albedo, the reflectivity of the ground before you put in the solar array versus what are you absorbing minus what you're exporting out of that like 20% or so. And what it comes to is if you're in a really sandy area, like in a lighter colored sand that has albedo of like 35%, you will create more heat by putting the solar array out at that location than if it wasn't there. But here's the big caveat, and this is where this person gets their arguments wrong because he tries to trash solar arrays for that reason, is his comparison should actually, and all comparisons should compare putting a solar array here and getting that same amount of electricity from a solar array versus there's the demand for that energy somewhere, and what if it came from coal instead, and how much does a coal plant radiate out in heat as well and cause additional warming due to CO2 emissions and that kind of stuff. But even if you just took the heat emitted out the stack and radiating out from the combustion chamber on a coal plant, putting a solar array on a highly reflective, high albedo, sandy surface is still equivalent or better than getting your power from coal.
Okay, so if it were on a darker surface, it wouldn't be as bad. Is that what you're
Right. In
saying?
fact, the darker the surface, any albedo lower than about 25, 28%, the solar array will have a net cooling effect just on the ground itself. And it's a higher net cooling effect when you take into account, well, are you using natural gas combustion or coal to generate that same amount of electricity?
I see. Okay, good. Because I know with agrivoltaics, um, the plant matter will cool down the panels as well, which is nice for efficiency.
Yeah,
Great, thank you.
sure. Yeah, and Remy points out that ideal steam engines only go up to like 45%. And there are things like combined cycle natural gas power plants, which personally I think if you're going to build a natural gas power plant, it should be illegal to do a single cycle. They should all be combined cycle. Combined cycle will produce 65% of the energy content of the fuel will go to producing electricity versus a single cycle will only be max 35%. Same amount of natural gas, and that's really it's a commons kind of everyone has some ownership in those natural resources. And if we're wasting almost half of it because we're not running it through the most efficient generation systems, that's stealing energy potential from everybody. So if you're going to build natural gas, do a combined cycle. And actually in Sweden, what they do, you'll see the thermal cycle engines they run, they don't burn natural gas or coal, they actually burn their combustible waste. And on those, they've kind of dialed them in where they actually they'll pull heat off of the engine and run that through district heating loops, both in industrial and business parks. And now they've expanded it to neighborhoods. So they'll have a buried insulated line carrying hot water coming off of that waste burning power plant. And they'll have these little stubs coming off the main line into houses and a metered heat exchanger. And so you never run out of hot water. And the efficiency of those is between 80 and 85%. They get about 20% of electricity and 60 to 65% heat value that is sold, and they get real community benefit from that heat. And then they don't have waste piling up in their landfills too. So it's a really efficient system. Sweden does a great job of that. So I guess to Carly's question of the heat created from the panel is mostly due to the dark color of the panel, and it's definitely the electricity is actually pulling heat off of that panel. So the more efficient it is, the more heat you're sending out to the grid. For that surface area, there's always the same amount of sun energy coming from the sun for that surface area. More efficient cells, more efficient modules take more of that heat and send it out to the grid. And if it didn't, though, then the module would heat up more. Great. Well, hopefully folks have come away knowing a little bit more about infrared than you started. It's a great tool. I use it a lot, and hopefully you'll dabble in it as well. It's pretty fun stuff. You know, Kajal, in fact, Kajal, I'll give you the task to go off and see if you can find any peer-reviewed research on quantum dots
Oh,
and how that might affect the infrared absorption of
well,
PVC. Because I do not know. I would have to look that up.
yeah. Okay, sure.
Oh, one last thing I'll add as people are dropping off is that if anyone has a solar array, small or large, you would like to showcase, we would love to have you be a guest presenter and give us the history of why did you put it in? What did you put in? What was the motivation? How's it performing? Those kind of things. We'd love to see your systems as well. So contact Kajal or myself. Kajal is the vice chair of the PV technical division, and we'll see about getting you on one of the future webinars.
Thank you so much, Rich. That was great.
All right. Well,
For
thanks
the-
everybody for coming.
Awesome. Have a great rest of your day, and be sure to submit an extended abstract if you're interested in participating in the Solar 2025 conference. I'll put it up in the follow-up notes later with the recording.
All right. See
All
you.
right, thank you.
Thank you. Bye. Thank you.
Thank you.